Hey there. So we're going to do a problem that is a simplified version of an alpha radioactive decay. Okay, and the problem is outlined here. And I put the problem statement in this time because I thought it would be useful to see the process of translating the written problem on, an assignment or a quiz or an exam into into mathematics that we end up solving. Okay, so what we've got here is an atomic nucleus is moving at 500 meters per second, emits an alpha particle in the direction of its velocity, and the new nucleus slows to 450 meters per second. Okay, and then we're given the masses in atomic mass units there, and asked for the speed of the alpha particle when it is emitted. So initially, the alpha particle and the original nucleus are all, they're all part of the same thing. And that whole thing is moving to the right, say, with some velocity I'll call initial velocity. And we're told that that initial velocity is 500 meters per second. And then after, well, so if this is before the alpha decay, then after, we've got the following situation. We've got a nucleus that has lost a little bit of its mass because it's kicked it off in the form of this alpha particle. And that's moving with some other velocity. We'll call it v final. And that is 450 meters per second, according to the problem. And we've also got this alpha particle, okay, which is moving with some unknown speed. That's what we're trying to find. And we're also told, right, that the mass of the alpha particle, let's say, like m sub a, is 4.0 u, so atomic mass units. And you can convert it to kilograms, but as we will see, we don't need to do that, okay? Mostly the proportion of the masses is the important part. And I'll say m sub n for nucleus, the original one, so up here, is 222 atomic mass units. All right, what do we use to solve this? Well, you could think about this like kind of like a collision, but it's more of just a conservation of momentum problem. But if we think about the various tools that we've used on situations like this, we have only two possibilities. One is conservation of mechanical energy, and the other is conservation of momentum. And because we're not given any information about whether this is an elastic interaction or an inelastic interaction, or collision, or whatever you want to call it, we must only assume that conservation of momentum applies. And we know that this is going to apply because in that instant where this thing is decaying into a daughter nucleus and an alpha particle, well, in that moment, the forces they are exerting on each other are huge, and things like the force of gravity or anything else that might be acting on these things are small. And so we can assume that the external forces from this system of two little particles are tiny, if not non-existent. And so we can rely on conservation of momentum. Just in terms of collisions, it's also the only thing that we can rely on that is true for both inelastic collisions and elastic collisions, whereas only conservation of mechanical energy will apply to elastic collisions, only that type. All right, so initial momentum of the system equals final momentum of the system. And if we just write that out for this problem, well, before, we've got just a single thing, the mass of the original nucleus times its velocity, v sub 0, which is 500 meters per second. Subatomic particles of this size really move along. They can move quite a bit faster than 500 meters per second, in fact. But that's what we've got here. And there's nothing else, right? It hasn't split apart yet, so that's the only term that you would appear on the left-hand side of the equation, the initial momentum of the system. Now, finally, we've got two different pieces. We've got the alpha particle, which is the mass of the alpha particle, times its velocity, the thing that we're trying to find. It's to the right, so I'm not having to put in different signs here for the velocities. And then we've also got the daughter nucleus, which in this simplified version of the problem is just going to be the original nucleus's mass, that 222 atomic mass units, minus whatever the mass of the alpha particle is, times its velocity, so v final. Okay. So how does this work out? Well, we're looking for this quantity right there, so we need to solve for it. And if we just check over the rest of the equation, we know this and this and this and this and this. We know everything else. Great. Okay, so we just need to solve for it and we'll be basically done. Let's see, what do we want to do? Well, we'll move first this thing to the other side, so subtract that from both sides. And then divide both sides by the mass of the alpha particle. That cancels it over here, puts it in the denominator over here. And then we can just substitute in for all of this stuff. So let's see if I can fit it in. So the mass of the original nucleus is 222. Initial velocity is 500 meters per second. Then 222 minus 4 for the daughter nucleus mass times 450 meters per second. All divided by the mass of the alpha particle, which is 4 atomic mass units. And that's going to be equal to the velocity of that alpha particle, right? What we're looking for in this problem. If you plug all of that in, okay, you should get approximately 2,200. I think it's actually a little bit higher than that here. Let's actually type it in live here. Let me erase that. Okay. So if we type it in live, we got 222 times 500 minus, then we put some parentheses in, 218 times 450. Divide that result by 4. And you get that the velocity of the alpha particle was 3,225 meters per second. Rounded to sig figs here, I guess you round it to more like 3,200 meters per second, okay? But this is reasonably close, okay? Now, a couple of things here. One, why didn't we convert to kilograms? Well, we could, but as you can see, we've got a ratio, right? We've got units of mass above, and we've got units of mass below in this algebraic expression. And so whatever the units of the mass is, as long as it's all the same unit, okay, we'll just have all those canceling out. So it's really just the proportion of the masses that matter. So we can just leave it in terms of atomic mass units and be fine. The other thing here is that if you remember maybe back to your chemistry class where you considered radioactive decays, you may have discussed the idea that when you have a decay like this, you don't just have a change of mass that is, the original nuclear mass minus whatever the mass is of the particle that left, right? That there's some amount of mass that is converted directly to energy and usually given off in the form of like a photon or the kinetic energy of the particles involved or something along those lines, okay? So the actual conservation of momentum problem here would be a bit more complicated than what we're looking at here, okay? So we're stripping it down to its basics, but also shows the mechanics of some conservation and momentum interaction like this. Hope this problem was useful, and we'll look at another one soon.